right? Which comes off a number line, which is one-dimensional. The output is a real number, right? Which again is one-dimensional. So in order to visualize this, we only need what? 2 dimensions, right? The input and the output. The problem with imaginary numbers is that when you talk about an imaginary number or complex numbers, here's an example of a complex number, 3 plus I. This is back from college algebra. That's an example of a complex number. In order to visualize that complex number, you actually need to draw 2 axes. One axis we call the real axis, the other one is the imaginary axis. So to visualize that number, I go to the right 3, and I go up 1, and I draw a dot. This dot in 2-dimensional space represents that number. You following me? So you need 2 dimensions to see what a complex number looks like. Now imagine some function that's going to take that number and do something to it, right? Square it, do something, right? It's going to spit out another complex number. And so the output is going to come over here, and I don't know, maybe it takes that number over to this point right there. So how many dimensions do you have for the input? 2. How many dimensions for the output?
2.
How am I ever going to get you to visualize that? You need 4 dimensions. 2 for the in and 2 for the out. You see that? Are you ready for that? So that's the thing. That's why we avoid the complex numbers for so long. That's why we go through the whole sequence of calculus. We get you to a point where, like, because you asked me, like, what do we do before computers to visualize, right? So, right? Well, yeah, we struggled. And that's why you avoid complex numbers, because then when we get there, there's nothing I can give you to show you it, right? We're not going to be able to visualize the function. It's going to be something very abstract. Yeah? And that's why it gets harder, because, I mean, when you're working in, I mean, we work comfortably in 3-dimensional space. We can see it, it's tangible to us, right? As soon as you go to 4-dimensional space, though, you know, you could say, oh, well, time is a 4th dimension. Fine, what about 5th-dimensional space? You know, I mean, what does 100-dimensional space look like? What does infinite dimensional space look like? These all have, like, solid mathematical, like, there's good reason to have it. Think about a function that would take in, I don't know, 30 variables in, 30 inputs, and give you maybe 5 outputs. Weather modeling, right? Trying to figure out, like, predict the weather, right? What do they look at? Inputs. What are the inputs? Temperature, pressure, humidity, right? All these inputs, right? Wind speed. And then they put that into a function, some model, and it spits out some answers, right? Okay, we think it's going to be this, right? Those are functions working in dimensions that you can't see, right? So it gets harder when you can't visualize. It does. So in Cal 3, we have the technology now where we can visualize a lot of what we do in here, which is great. So anyway, all right. I just wanted you to see why we don't study complex numbers. If you've ever wondered, because complex numbers are extremely important. Like, I was having this conversation with my daughter the other night. Like, imaginary numbers, they get a bad rap, don't they? Because everyone thinks they're just made up, like, fictitious stuff, right? Like my imaginary friend that sits on my shoulder, and everyone's just like, okay, weirdo, right? But complex numbers are just as important and just as real as the numbers you use, right? Just as important. Some of the most, like, fundamental equations that we use in, like, physics and engineering involve imaginary numbers. Do I stop? Do I continue? A little bit? Just a little? Why is it that imaginary numbers got such a bad rap in the beginning? In the beginning, it came from the idea of a parabola. And we found, and hopefully your college algebra teacher, professor showed you this, that all quadratic equations of the form ax squared plus bx plus c equals 0, all quadratic equations have solutions using that formula. And that can be proven. I could show that to you in class. We could derive the formula, but we're not going to. So trusting that that formula is true, what happened back in history is that we got to a point where we're like, okay, well, what about this? What are the x-intercepts of this? Well, there aren't, right? And if you try and use this formula, what happens here? How do you know that you don't have x-intercepts in this formula? What's going to happen? you're going to wind up getting a negative under here. That discriminant's going to be negative. And so for a long time, mathematicians were like, yeah, I mean, look, we're trying to figure out where this hits the x-axis, and there aren't any answers because we have to take the square root of a negative number. And so people are like, yeah, okay, that all makes sense. Well, then came along another equation for a cubic. So we don't study this at all, but that's a cubic equation, all right? And the cubic equation has a formula just like the quadratic equation has, all right? Y'all want to see it? Wait till I show it. Then you'll see why I don't know it.
What the heck?
Okay, there it is.
Nice.
Okay, that is the cubic equation. If you want to solve this equation, you need to know A, B, C, and D, right? And then you need to plug into that. Okay? You see why I don't know it? Okay. All right, so here's the thing about this equation. Hold on, there's something missing. Okay, there it is. All right. So do you see that in this equation, there are some places where you have square roots? You see the square root there? This is a cube root, but in here there's some square roots. Somebody was able to show a problem where they used this formula and what was underneath this root was negative. Okay? And they're like, well, what do I do? I've got a negative under there. Well, back with the parabola, what did the picture look like? We would say, okay, if you get a negative under there, that means your parabola is not going to hit the x-axis, right? But what can you tell me about every cubic polynomial? It has to hit the x-axis somewhere. Why? Because when you think about cubic polynomials, the degree is odd, which means your left side goes down, your right side goes up, or the other scenario it goes this, like this, right? One or the other. That means it's got to go through. You have to have an x-intercept. There's no way to avoid it, which meant that the negatives under here had to have meaning. Does that make sense? Whereas with the parabola, we could just kind of like dismiss it and be like, well, yeah, there's no answers. And the negative under the root's telling us that there's no answers, which was great until we got to this. I hope that makes sense to you. So once they figured that, I said, oh shit, we have to take this seriously now. It already had a bad rap. It was already kind of like imaginary numbers, okay. But it turns out that they're actually really important. Okay, do you think there's one for a fourth degree? You want to see it? Okay, so what is fourth degree called? No, quad, cubic, quartic equation. Dun, 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 dun. I don't even know if we're going to be able to find it. Let's see. I'm just going to some random site here. I don't even think that's it. Yeah, that's not it.
Wouldn't you look up like solutions for? There you go.
Let's go here. That's the cubic. Hold on. I've seen it before. So fourth degree equation formula. Images. There it is. Where is it?
I wish I never had to ask that question.
There. Okay, there it is. So if you have like ax to the fourth plus bx to the third plus cx, right?
You know that dude figured this out in no personal life.
Most mathematicians don't. All right, so there's your fourth. You don't want to see the fifth? No? So here, this is why I brought this up. There is no fifth. Okay, and it's not because it hasn't been found. it's been proven it doesn't exist. There's a difference between those two statements, right? To say, hey, we've never been able to find the fifth degree equation, we've never been able to discover it. No, it's been proven that it can't exist. So we only have formulas up to fourth degree polynomial equations. That's all. That's all we'll ever have. Kind of interesting, huh? Okay, we're going back to our notes. Well, I went way off just by showing y'all GeoGebra. All right, let's continue. I'm going to let you think about this one. And why don't you start working on this? I'm going to go get a drink. Why don't y'all see if you can figure this out together or alone. I don't care how you work. I'll give you a few minutes. Think through the problem. Don't just start cranking stuff out. Find the equation of the plane through these 3 points. I'm giving you 3 points. I want the equation of the plane. Try using what we've learned in here. I'll be right back. This a little bit. As of right now, what have we been able to do in terms of the equation of a plane? I gave you what? A point and the normal vector. If that's what we have, we're in business, right? But I don't give you that here, right? I give you what? 3 points. So just imagine those 3 points. Let me put them on this plane. I'm assuming y'all are kind of struggling with this just by the look of. You have an idea? Okay, I'll let you tell me. I have 3 points, right? So we know how to do this if we have 1 point in a normal vector. I've got 3 points, so this is like overkill. I've got so many points, right? So I just pick one of them as 1 point. Now what about the normal vector? What are you thinking?
So what I was thinking was making 2 vectors and then finding the cross product.
Exactly. So look, we have 3 points, right? We need a vector that comes out of this plane orthogonal. So what we can do is we can create a vector going from 1 point to the other, another vector going from 1 point to the other. Doesn't matter how we do this. Take those 2 vectors, take their cross product, and that will generate a vector pointing out of this plane orthogonal to it, right? So that's how you're going to get your normal vector. So we pick 1 point as our base point. Did that make sense to everyone? Yep. Yes? Okay. So what point do y'all want to use as our base point? Yeah, let's just call this our x naught, y naught, z naught, right? Okay, that's going to be our point. That's going to go into this formula. But how do we get the normal vector? The normal vector is going to be achieved by taking 2 vectors and crossing them, right? We're going to cross 2 vectors. But we have to get these vectors, right? And how do you create these vectors if all you have are points? We've done this. Yeah, subtract, right? Do that thing. So why don't we Why don't y'all give me the vector that goes from here to here? What's that vector that goes from our base point to that point? -3, -7, -15. And we've got to cross that with, now let's do the vector that goes from here to that one. 11, -5, -13. Boom. And now, I think the rest of this is just arithmetic, right? We know how to do cross products. That's where you do that thing with the determinants. Or use your calculator, right? Do your cross product, you're going to get a vector. Once you have that vector, well, you just plug in and we're done. Okay, so let me do a cross product using online software. So let's go to Wolfram. I'm going to have it do the cross of, I don't know how they want me to put vectors in here, but I'm sure it'll understand. -3, -7. I'm doing it on the calculator because given enough time, you could do it by hand. And then 11, -5, -13. I think we're going to get big numbers here.
It's -15 or something.
Oh, is it negative?
Yeah, the first one's
Oh, I messed up. Negative. Let's see if it understood that. -16, or sorry, 16, -204.92. 16, -204.92. Oops, wrong one. Now, yeah, I was going to say, we can do any vector that's orthogonal. So we can do any scalar multiple of this. So let's try and make it nicer. So I'll say, or we could do, let's divide everything by 2. We get 8, what is that, -102, 45, 46. Go again. Okay, 4, 51, -51, 23.
5 by 2 again.
Yeah, no, thank you. I think we're good. That's just a smaller vector. It doesn't matter, just any normal vector. And so now the equation. So I'm just going to plug into this. Okay, so I'm going to use this as my A, B, C. So 4 parentheses x minus 1. And then -51, and then y minus 2. And then plus 23, and then z minus 14. Yes?
Does a cross product give you a vector or a point?
A vector. A vector. The dot product of two vectors gives you a number, right? And the cross product of two vectors gives you a vector. And that was the most, I said, if there's one thing that you need to know about the cross product of two vectors, is that when you cross two vectors, you get this vector that's orthogonal to both. And that's what we're using here, is that the cross product always gives you a vector orthogonal to both vectors, which is exactly what we need for that normal vector to be sticking out of the plane. Do y'all see why it didn't matter that I scale this, that it has no impact on this equation? Right now, if I wanted to get back to this one, like instead of using this vector, I use that one. What do I do here? Multiply both sides by 2, and it has no impact on the right-hand side, you see? So multiplying by 2 doesn't change the equation. Multiplying by 5 doesn't change the equation. So it can be any multiple of that vector. What I've always found kind of a little mind-boggling is that when I wrote this equation down, this right here could have been any of these points. It didn't have to be 1, 2, 4, or 14. You could have done what? +2, +5, +1, and it still would have been the same equation, which is, I've always felt is real weird. But what should be the same for all of us, even though this might look a little different for all of us, if we multiply through and clean up, we should all have the same equation. All right, the angle between two planes. How are we doing on time? 15 minutes? The angle between two planes. So let's say that we have two planes, all right? two separate different planes, distinct planes, and we want to find the angle between them. So I'll take a simple case. Let's say we have this plane, right, flat, and we have this plane right here, boom, like this. What's the angle between them? 90 degrees, right? They're orthogonal, right? And the way you can see that is actually by comparing their whats. I can't do it. They're normals, right? What is the normal of this plane? It's like this, right? And then what is the normal of this one? Straight up like this, like that, right? Sorry, yes? So if I compare the two normals, here's what they would look like. And the normals are orthogonal, which means the planes are orthogonal. In fact, the angle between the normals is equivalent to the angle between the planes. And so that's how we can always find the angle between two planes, is just by finding the angle between the two normals. And have we talked about how to find the angle between two vectors? Yeah, there was a formula, wasn't there? There was a formula. It said if you're given two vectors, u and v, right? Given two vectors, the angle between them is theta equals, do you remember it? No? Cosine inverse, drum roll, dot product divided by the lengths of each one. Okay, there was a formula in our notes from last week that if you're trying to find the angle between two vectors, you're just going to dot the two vectors, you're going to divide by the lengths of the two vectors being multiplied together, take that, take arc cosine of that, and that'll give you the angle between the two vectors. Okay, now in this case, we would do the angle between the two normals. So it'd be the first normal and the second normal, and we just do the same formula. This is just a visualization of this. Here's two planes. Do you all see the two planes? And if we're trying to find the angle between them, we first look at their normals. Do you all agree that that orange is normal to that? And then if I turn the green is normal, I think. And so what I can do is I can move the normals so that they're tail to tail. Get rid of them there. So I just move them tail to tail, and the angle between those two, there we go. This angle between the two normals is equivalent to the angle between the two vectors. Between the two planes. Okay. This is just a result. Two planes are parallel if and only if their normal vectors are parallel. In other words, their normal vectors are scalar multiples. I think that's pretty self-explanatory. Two planes are perpendicular if and only if their normals are orthogonal. So if you take two planes and you dot their normals and you get 0, they're perpendicular planes. Let's check that real quick. What is the normal vector to the xy plane? To the xy plane. What's the normal? What is a normal vector coming out of the xy plane? Give me any normal vector coming out of the xy plane. Any vector that just points straight up like that.
Y equals 4.
No?
Z equals 1.
004 or 001 or 002, right? So let's imagine we had that. I heard 004 first. Okay, that's a normal vector for this, right? And then how about the normal vector of this plane right here? So that's x, this is y, this is z. 0, 1, 0. What happens if I dot those? I get 0, right? They're orthogonal. Here, orthogonal. So that's a property of any two planes. You dot their normals. If you get 0, they're orthogonal. Find the angle between these planes. Find the angle between these two planes. All right, so can you tell me the normal vector of this plane, this first plane? What do you notice about the generic equation of a plane? The A goes through, the B goes through, the C goes through. The coefficients in front of x, y, and z respectively are the x, y, and z components of the normal vector. So this has a 1 here, a 1 here, and a 1 here, which means the normal vector of this plane is the vector 1, 1, 1. Right? The vector 1, 1, 1. What is the normal vector of the second plane? 2, -4, 7, right? It's just the coefficients in front of the x, y, and z respectively. We don't care about this number. We care about the coefficients in front of the x, y, z. Okay, so what's the angle between those? Well, we have to do theta equals cosine inverse of, we got to take the two vectors and dot them. And then we have to find the magnitude of each of them. So magnitude, square root of 1 squared plus 1 squared plus 1 squared times square root of 2 squared plus -4 squared plus, I'm out of room, 7 squared. Do y'all understand what I'm doing at least? Yeah, I've got to dot them, figure it out, then find these lengths, get that as a number, plug that into my calculator. Make sure I know if I'm in radians or degrees, because if I'm in radians, my answer is going to be in radians, and if I'm in degrees, my answer is going to be in degrees, right? So we need to state that in our answer. I'm not going to calculate that, because I think that that's just a computational thing that you could do, right? Any questions on that? If you're looking at a plane equation, do y'all see how easy it is to identify the normal vector? Super straightforward. Just look at the coefficients of x, y, and z respectively. I'm almost out of time, but I want to get to this last thing here. The line of intersection of two planes. So I'm going to show you the visual of this in a second, but I want to see if we can deduce it without the visual aid. Let's say we have two planes, and they hit each other, intersect. And I'm not saying they're orthogonal, they just intersect each other, right? In this case, the way I have it here, they're intersecting each other in what? Like, what does their intersection look like to you? A line. Do you all agree that there is a line of intersection of these two planes? What's the vector equation of that line? That's the question. We just studied lines, right? And for any line, we can find the vector equation of a line? Yes? Okay. But what do we need for the vector equation of a line? Or a point and direction vector, right? So recap, for the vector equation of a line, you need either 2 points or you need a point and a direction vector, yes? Okay, I'm about to give you two planes, which means I'm going to give you two equations. You see these two equations? We'll probably just work with that. These are two planes, right? Are these planes orthogonal to one another? Are they? Check. Dot the normals. It's not 0. Okay, so these are not orthogonal. They're at an angle. They hit each other in a line. I want the equation of that line. That seems challenging, yes? That seems very challenging. Does that not seem challenging? Okay, watch how we're going to do it. First of all, let's stick with this example right here. If these two hit each other, right? If these two hit each other, then there's some point, there's a bunch of points that are on both of the planes, right? Yeah. So can you just like think of a way that you could find one of those points? Like, can you find me any point of intersection? How would you go about doing it? If you set these planes equal to one another, you're going to have one equation and three unknowns, right? So you would right now we have how many equations? 2. How many unknowns? 3. So if you have 3 unknowns and 2 equations, it's possible to have infinite number of solutions. So see, right now what I'm trying to do is, again, I'm trying to get you to see that if we have 2 planes that hit each other, it's really hard to draw this. 2 planes that hit each other, they're going to hit each other in a line, right? They're going to hit in a line. And what I'm trying to do is just find me a point. Just give me any point on that line, because I need a point and then I need a direction vector, right? To define a line. At least let me see if I can even get a point, right? So here's how I'm going to get the point. I'm going to be clever, and I'm just going to say, look at that over there. Let's just let, I don't know, let's let z be 0. Let's just pick. Let's just let z be 0. If I let z be 0, what do these two equations become? X plus y equals 5, and the other one? 2x minus 4y minus 10 equals 0. Can I just move the 10 to the other side? Then we have this, right? Now we have two equations and two unknowns. Can we solve that? Yeah. We should be able to get a solution here. See, I picked any value of z I wanted. I could have said, let z be 2. I could have said, let x be 1, let x be 0, let y be 5, let z be pi. I could have done anything I wanted. I chose z 0 because it kills z off, right? And now I reduce this here. So let's solve this. How would you solve that? Solve for y. So you do substitution? There's different ways. I would do elimination. I would maybe multiply the top one by 4. 20. Just scaling the first one. And then add straight down. And I get like 6x equals, the 4's cancel, I get 30. Ooh, x is 5. Beautiful. X is 5. And once I know what x is, I can go back to either one of the equations. Y is what? Y is 0? Really? Is it? Yeah, I think it is, right? So that implies y is 0. So have I found a point that is on the intersection of those two? No, that's not a point? It doesn't satisfy both?
I guess what about the z?
Hold on. Z was 0, remember? Z was 0. So I have x was 5, y was 0, and z was 0. So is that point on the intersection of these planes? Yep. 5, 0, 0. Yep. And then how about 5, 0, 0? 2 times 5 is 10. 10 minus 10. It works, right? I found a point that satisfies both. Okay, so do I have a point on the line of intersection? Yes. All I need now is what? A direction vector of the line. Where is that going to come from? Drum roll. How? What with the normals? We have two normals, don't we? I need help. Will you help? Will you help? Will you help? Yeah, hold that plane and hold that normal. You can stand up. Here, come over here so you're not on camera. All right, there we go. Y'all see that? Okay, we have another plane. These need to intersect. So let's tilt this down a little bit. Okay, here we go. Right there. You just stay. All right, can you all see that? I'm going to move to like that. Can you all see this line of intersection of these two? We're trying to find the direction of this line. And there's your normal and there's my normal. Bring your normal down.